Hello, my name is Nathan Schimpf, and I'll be presenting to you today about my final project, which was the use of different forms of genetic algorithms for the maximum clique problem. Before we get into the problem itself, I did just want to review a little bit of graph theory to make sure everyone's on the same page. Graphs are typically defined as a set of nodes and a set of edges. The nodes, which are listed as V, can typically just be a list, whereas the edges are typically represented as what's called an adjacency matrix, which you see pictured. This would be an n by n matrix, in this case 5 by 5, where each element corresponds to whether or not an edge is present between those two nodes. So in this case, we can see between node 1 and node 3 there is an edge, which is true. Complete subgraph and subgraph. So a subgraph is a subset of nodes from your original graph and the edges that are associated with it. For it to be complete is just an extra stipulation around the uniqueness of those edges. And finally, a clique would be a complete subgraph where every node is adjacent to one another. And in this case, you can see that pictured in red. For the maximum clique problem, this kind of should have a bit of intuition going off of that previous slide. Basically, it poses that given a graph G, what is the largest subgraph that can be generated, such that that subgraph is a clique. Typically, we define that clique as having a size of k. This is actually not the only problem that's kind of posed this way within graph theory. There's a couple of variations I wanted to briefly mention. The clique decision problem is a slightly more rigorous form of the maximum clique problem. Basically, it asks, given a graph, does a clique of size k exist within it? The maximum independent set problem kind of poses the inverse of the maximum clique problem. So given a graph, what is the largest number of nodes present in a subgraph without any of them connecting to one another? Finally, there's the maximum cover problem, which kind of looks at the subsets of graphs and tries to find the largest coverage of your original graph by using only so many of those subgraphs. These problems all are applied to several different fields. Bioinformatics and chemistry come up sometimes. I've mostly known about it in terms of communications and networking, where it's been applied to channel coding, channel allocation, and some throughput design and analysis. I considered a total of 5 approaches to the maximum clique problem. These included one heuristic solution, which was the worst out heuristic. We'll discuss that shortly, as well as 4 different genetic algorithm variations, 3 of which were based on the Back Khuri fitness, and 1 of which was based on the heuristic genetic algorithm, which was proposed by Marchiori. The variations of genetic algorithms included the standard genetic algorithm, so generating a population at random, assessing the fitness of that population, and then kind of combining individuals from that population to generate better solutions, and of course incorporating some sort of mutation or slight changes to allow for variance as evolution occurs. Wisdom of crowds is an extension of the standard genetic algorithm, where an agreement matrix is generated from your solutions to try and represent the probability of each solution. From that, typically you try to sample to generate an average of your total set of solutions, which for larger problems is actually able to improve over any individual solution. Finally, the compact genetic algorithm takes this idea from wisdom of crowds of using an agreement matrix and implements it directly in place of a population. So to kind of represent that, you would actually have a set of probabilities that you would be sampling from to create individuals that you would assess the fitness of. Based on those samples, you can then kind of determine what changes need to happen to your probability matrix to better represent the likelihood of certain solutions. The first approach that I considered was the heuristic search. There are two that are commonly referenced in literature, the best in search and the worst out search. Best in search would start with an empty subgraph and slowly incorporate nodes, ensuring that every added node maintains a clique. The worst out subgraph is what you see visualized here, where you start with a complete graph as your subgraph, and you remove nodes until you are left with a clique. To do this, I used the cost estimate, that is edge densities, so choosing the nodes with the smallest edge density to remove. This is probably a naive approach, a fairly straightforward approach. While it will always find a clique, it is rarely going to find an optimal solution. And because of this, I really used it just as an analog to the lower bound when that wasn't available for data. The first genetic algorithm approach that I wanted to discuss was proposed by Back Khuri, I believe in 1992. This was actually proposed for the maximum independent set problem, but it can be used for maximum clique, given that you kind of are learning with the complement of the graph. Basically, the solution is a general purpose genetic algorithm with a specific fitness function that allows for learning legal solutions and then extending that into meaningful solutions. This is a graded penalty, which you see as the equation, where again, for the maximum independent set problem in this case, if there's a node incorporated that prevents independence, then that would cause a much harsher penalty to be added to your solution fitness. Because of that, again, the genetic algorithms are able to quickly learn a legal solution. And then once that's learned, it's able to kind of fine-tune that by looking at the value of those legal solutions to learn more meaningful solutions. The alternative approach that I wanted to discuss, and this was kind of something I implemented towards the end, was the heuristic genetic algorithm, which was proposed by Marchiori a few years later. This approach considers a genetic algorithm where before assessing the fitness, but after generating your population or updating your population, you repair each of your solutions into legal solutions. So in this case, that would mean that you would look at your subgraphs and kind of prune them down into cliques, and then try to extend that clique with nodes that you kind of verify as being useful. Because of this, it doesn't need a graded penalty as the fitness function, and can simply just be based on the size of the clique that it is providing as a solution. For my experiments, I considered the same parameters that were proposed by Back and Khuri with their paper, because most of my solutions are based on their paper originally. I looked at two different data sets and collected a small number of graphs from each of them, those being the Rutgers Maximum Clique Challenge from 1992. These are generated graphs, and they were used extensively for the maximum clique research for that decade, really. After that, I incorporated a couple of graphs from the Koblenz Network Collective, which to my knowledge is still being maintained. And these graphs are actually observations from real-world data and real-world relationships. For example, trade between cities, or the relationships between characters within a novel. Looking at these solutions from the DIMACS data challenge, there's a couple of trends that I do want to point out. First of all, with the worst out heuristic, we can see that it does typically generate a solution, but the solution is rarely optimal, if ever optimal. Again, I incorporated this as a baseline and kind of a reference point if there was no lower bound known. The other main issue with this heuristic is that it is, of course, time inefficient. This is not uncommon for search heuristics of this nature. And because of that, it's not useful once we start dealing with larger graphs. With the first genetic algorithm, it does solve one of these problems. Unfortunately, it's not the most meaningful of problems that it solves, which is the time it takes to actually iterate through and generate a solution. It's able to generally do that within a consistent time frame. However, these solutions are never optimal, always at least trivial, and sometimes not even legal. And because of that, it's not a useful method, really. Sometimes it does take, out of the genetic algorithms, the longest time to converge as well. Looking at the wisdom of crowds, it improves on one of those things, but it's, again, not the most interesting, and that is the time it takes to converge. For larger solutions, it is able to converge to a solution faster in terms of generations. Execution time stays roughly the same, but not particularly better. However, the solutions are still not are still trivial, and often are still not legal, significantly more so than before. Looking at the compact genetic algorithm, we start to see more meaningful changes, but again, not what we would like to see. No longer are we getting illegal solutions, but we're still not getting non-trivial solutions. The convergence time stays useful. The execution time is very fast. So theoretically, this framework is a solid foundation, but there's still something going wrong, which we see solved with using the heuristic genetic algorithm proposed by Marchiori. At this point, we actually see non-trivial solutions every time, even though the execution time starts to increase noticeably. These trends continue for the KONECT graphs. I just wanted to point out that the Marchiori solution is not always the best out of these, so it's not uniformly better than, for example, the worst out heuristic. We can see that with the Arenas Jazz graph, which is representing the relationship between, or the collaborations between different jazz musicians at the time it was collected. In this case, the worst out heuristic actually gets a click size of 8 as opposed to the click size of 6 found by Marchiori. So why do these Back Khuri genetic algorithms fail for this problem? First of all, it's possible and likely that there's some implementation challenges that I ran into and was not able to solve. But one of the major issues is actually the graded penalty itself. While it ensures legal solutions, it also, especially for larger problems, ensures that trivial solutions are kind of selected as well. Basically, as we are generating routes, it's almost guaranteed that we're going to end up generating routes that are too large and therefore illegal when we get to these larger graphs. Because of that, because every graph is going to likely be illegal in some way, this forces harsh penalties on almost every node in the graph, and therefore forces the genetic algorithm to kind of be learning to not choose any nodes at all. And that's most pronounced with the compact genetic algorithm. As you can see, it very quickly learns that the optimal solution in its case is not a solution, to propose no nodes as a clique. Marchiori, of course, solves this because of the heuristic algorithm, which forces non-trivial solutions to be provided before fitness assessment and updates to the population. But there were still some implementation issues that I didn't resolve. First of all, as you can see from its training graph, it was not convergent. This is because of some oversights that I had with the population updating. I still was using what I had to use for the Back Khuri fitness, where updating the population was based directly on that fitness score. And as a result, these updates never actually penalized the Marchiori solutions, which meant that any sample could still be re-included in the graph. Any node could be re-included, really. The other issue, not as significant but still noteworthy, was that I chose the simplest possible solution for the heuristic implementation. Marchiori proposed probably 3 or 4 different ways to prune graphs into a clique, as well as to extend graphs, and I more or less chose to choose nodes at random to accomplish this. Because of that, it's likely that the legal solutions that were found were much smaller than they could have actually been, or much smaller than the optimal solutions, or even the solutions that the generic algorithm could have found. However, this final project does illustrate the importance of using heuristics and incorporating them with generic algorithms. It illustrates the limitations of generic algorithms, where they can learn to find meaningful solutions, they can learn to find solutions very effectively, but they need some level of support to do so meaningfully. In my case, Back Khuri Fitness and its generic algorithms that I tried were over-reliant on evolutionary learning, and as a result prevented learning meaningful solutions, and rather instead found trivial. The incorporation of heuristics with Marchiori circumnavigated that and allowed for meaningful clique sizes to be found. That is all I wanted to present to you today. If you have any questions, feel free to email me. Thank you for your time.